So here's a table of requirements for a headpiece and point the support on for the different basic types. So in a basic type 1, so this is 2, 3, and 4 runs across the top. The next column is which portion of the headpiece we use, which support. Then obviously these are the levels of the skull that would be supported. And then whether the head is tilted, I'm sorry, the headpiece is tilted or set level. So in a basic type 1, depending on how much of a misalignment there is, you would use either the A support or you could use the middle of the square headpiece at B. And so you would set level area 1 on the diagram that we had prior. That would be this one here. So for basic type 1, we would be setting this area here. So the A support would be roughly somewhere in here. So it's supporting that portion, and the center of gravity being roughly between the eyes. So, and of course then, like we demonstrated earlier, the headpiece would not get tilted. So for a basic type 2, typically you would use the rounded headpiece, and you would then set the tip of the mastoid. We'll go back to that slide in just a second, palpating that. And then the parietal portion would be tipped. So when we go back to this one, you can see that I've outlined the tip of the mastoid here, and so you would set the rounded support here. So you can see that if the pivot is here, that the center of gravity is here, so that there's some leverage available to play with in terms of getting the head to move in a type 2 subluxation. So in a basic type 3, remember this is the type, first of all, it's relatively rare, only 7%, and there's no cervical line angle, so that the cervical line comes up to the atlas plane line perpendicularly. So typically we would use the D support on it, but you can also use C, which is the distal end coming from the bottom of the square support. And of course you would set more the body of the mastoid. So once again, going back to this slide, you wouldn't necessarily want to have quite this mechanical advantage as for a type 2. So rather than setting the very tip of the mastoid, you might set it more in the body of the mastoid, closer to the occipital portion of the skull. And you would also tip the parietals, but probably less than you would for a basic type 2, because in a type 2, the tipping of the head, or the falling of the head during the adjustment away from the side of laterality, will also power the reduction of the lower angle, whereas in a type 3, we don't want that since there is no cervical line or lower angle. So in that case, the tipping of the head would be somewhat less, so that you didn't have quite as much movement of the head. In a basic type 4, now remember the 4 is a combination where the head is acting like a type 2, but the rest of the subluxation looks like a basic type 1. So here, typically, you would set C. The choice for that would be because you want the center of gravity still up high enough to allow the head to turn, but not enough to power the reduction of the cervical line, because the direction that moves would be opposite of what our goal is. So, and you would set the area of the skull that's labeled as 4, which in this case is on the opposite side of the center of gravity. So C support would be here. Center of gravity is a little bit above that, and so then the head would still want to roll out, but much less quickly as it would if you were to support the very tip or even the body as in a type 3. Plus, the movement would be more slowed additionally by the use of the square rather than the round support. And you would still, though, tip it a little bit to allow some room for the head to move in that plane. So this is what it actually looks like. So in a basic type 1, this is the position of the patient. So what you note is that the glabella, nose, chin, and episternal notch are all aligned in a horizontal plane. We also check the back of the patient checking the center of the occiput and the VP to make sure that that's horizontal. The patient must be in a neutral position. You'll notice that the shoulders are also symmetrical, that the shoulders neither pulled down nor is it rotated forward or back, or kind of bunched up against the lower angle. And the EOP and VP must also align horizontally. You'll also notice in a basic type 1 that the center of gravity of the skull, which is between the eyes, falls on the A portion, probably right between A and B here. And that you'll also notice that the headpiece, excuse me, is horizontal in this case. So basic type 2 and 3 are similar enough that it's really more of an experiential difference than a visual one. So in this case, you would use the D support. So I've rotated the headpiece. So A, B, and C are here. This is the D support here, the rounded support. And you can see how far down it is relative to the patient's location, that it's roughly in line with the tip of the mastoid. And, of course, you palpate that for the proper position. Also notice that, once again, even though it's a basic type 2, the glabella, the nose, chin, and episteral notch are still aligned horizontally. There isn't kind of no preset to allow the head to roll. That happens during the adjustment, not in the setup. And, of course, the VP and external occipital protuberance, if it's on midline, should also be aligned in a horizontal orientation. And so, once again, this is lowered a bit to allow the head. So the doctor can scoot his fingers underneath the patient's parietals here to make sure that there's some free play in there to allow the head to move. So back to the square support for basic type 4, what we have now is that you can see that the center of gravity of the skull, which is between the eyes, is near the C support, or up even a little bit higher than that. You can see once again that the glabella, nose, chin, and episteral notch are aligned horizontally, and that in this case the parietals have been relieved. In other words, that the distal end of the headpiece has been lowered to allow the head to roll with that subluxation. And of course, once again, checking the back for the EOP and VP to be horizontally aligned is also critical. So this, once again, is the same diagram that I had before. So we have a height vector that has a positive value or a negative value if it's calculated as such. And then the rotational vector has an anterior component or a posterior component. And these are calculated off of the nasium and vertex, respectively. So this is the same model we had, so we won't spend too much time on this. But the composite of the height vector and the rotation vector, to reiterate, is called the horizontal resultant, and that's this HR. So that's this green line here. And it's horizontal because, once again, the patient is in side posture, so we're dealing with the horizontal plane here. And the length is the square root of the squared sums of the height vector and rotation vector. We went over that. And the direction is also a composite of these vectors. In other words, so it's not only the length that's important, but also its orientation relative to the patient. So the rotational vector, as we saw in the previous slide, is horizontally aligned, and the height vector is vertically aligned. So when we get to this slide, the height vector and rotation vector, these are not arbitrary. These are actually, this is the horizontal plane, and this is the vertical plane. And so this is a composite vector which has both of those components in it. So this then represents also, we've drawn in the Saddleback point. Now this is not to scale, this would be a very small listing. But so here's the contact point. So we calculate the height vector as a superior value in this case. We have an anterior value for the rotation value. And so then the horizontal resultant, some doctors even use a grid that has inch squares on it, and so then that's used to overlay the patient in side posture, and then a marker is placed at the saddleback point, and then you can then actually measure the length of the horizontal resultant rather than calculate it. But either way, it's important to know both its length and its direction. It is, after all, a vector quantity.